Good morning, everyone. Today's class, I'm going to discuss about nMOS fabrication processing. In last class, we discussed basic MOS transistors, what are the types of the MOS transistors, and also the operation of enhancement mode transistor, depletion mode transistor, how they are going to be work based on the some conditions. Okay, all those things we are discussing in previous class. Now I'm going to discuss about nMOS fabrication processing techniques, how the mass transistor is going to be formed based on some fabrication processing techniques. So here, these are the contents having in this nMOS fabrication processing techniques, such as first thing is basic process involved in fabricating. Means, so what are the methods and what are the techniques we need to apply for this fabrication processing techniques? And second thing is nMOS fabrication steps. So what are the steps we have to develop this nMOS fabrication processing? And next, nMOS fabrication processing with step by step. So what we discuss in nMOS fabrication steps, those are discussed step by step along with diagram. And next thing is the complete summary what we have done in this nMOS fabrication processing design. We need to summarize all the processing steps. So here, this is the basic processes involved in fabrication processing takes. Here, the first step is, in the first step, we need to consider one layer, nothing but silicon vapor. We need to cut some single crystal of silicon layer. So here it is called as substrate. And then masking. So here, what we need to form in particular CMOS structure, what are the layers, what are the regions to be needed to make the connections. Those are formed by using masking techniques. And photolithography to cover the entire surface for the required thickness. And the oxidation, there are two types of oxidation processing here. Next one is diffusion. Diffusion means to diffuse the diffusion impurities such as n-type, n plus diffusion impurities, and some of the p-type impurities are added in substrate, and some of the n plus diffusion impurities are diffused into the p-type substrate to form the source and dry regions. And next thing is etching. So for the formation of these fabrication processing techniques, the unwanted layers are need to be etched together to form the source and drain region. Next one is polysilicon gate. To make the connection gate, we need to cover the entire surface of the polysilicon gate. And finally, we need to get the terminals, source, gate, and drain. Then, before going to, then we need to metallize the entire surface with this metallization process, right? And these are the steps we are going to be discuss along with the diagram also. So here, before going to be discuss in detail with the diagram oriented, now I am going to discuss about step by point by point. That is 9 points here we need to discuss here. The first point is, firstly, processing is carried out on a thin vapor cut from a single crystal of silicon of high purity into which the required P impurities are introduced as the crystal is grown. Okay, simply I want to take one layer here that will be cut from crystal of silicon, single crystal of silicon here, and we need to improve the purity of the particular silicon crystal of layer or vapor to add some P-type impurities. Okay, then it will be increase the impurity concentration here. And second point is a layer of silicon dioxide that is grown all over the surface of the vapor to protect the surface, act as barrier dopants during the processing, and provide a generally insulating substrate onto which other layers may be deposited and patterned. And third point is the surface is now covered with a photoresist which is deposited onto the vapor and spun to achieve an even distribution of required thickness. Okay, if there is any up and downs on the surface of this layer. So we need to require a flattened and required thickness. We need to cover the entire surface with this photoresist layer. And fourth step is the photoresist layer is then exposed to ultraviolet light through a suitable mask, which defines those regions into which diffusion is take place together with transistor channel. Okay, so by this suitable masking process, we need to form the transistor is going to be in fabrication processing techniques. Okay, and next one is the fifth step is these areas are subsequently etched away together with underlying silicon dioxide so that the vapor surface is exposed in the window defined by the mask. So where we need to form that source, gate, and drain regions at that area, we need to be removed away together after processing the masking and photoresist layer. And sixth step is the remaining photoresist is removed and a thin layer of silicon dioxide is grown over the entire chip surface and the polysilicon is deposited on top of this to form the gate structure. Okay. And further, the photoresist coating and masking allows the polysilicon to be patterned, and then the thin oxide is removed and exposed areas into which n-type impurities are to be diffused to form the source and drain region. By using gas processing techniques, the n-type impurities are diffused into these p-type silicon substrate to form the source and drain region. And next, the thick oxide is grown overall again and then a masked with the photoresist and etched to expose selected areas of polysilicon gate and the drain source areas where we need to be make the connections, right? And ninth step is the whole chip then has metal deposited over its surface. This metal layer is then masked and etched to form the required connections pattern. So here the metal layer is taken it as a aluminum layer. That layer is covered the entire surface of the surface of silicon crystal where we need to make the connection. That connections are nothing but source, gate, and drain. The remaining areas is shielded, right? The first step here it is firstly the processing is carried out on a thin vapor cut of single crystal of silicon and such vapor surface is typically 75 to 150 mm in diameter and 0.4 mm in thickness. So this is the layer here. This is a p-type substrate, single crystal of silicon substrate with p-type impurities lightly doped here to improve the impurity here. So here the second point is with high purity into which the required p impurities are introduced as the crystal is grown and are doped with say boron impurities concentration that is 10 power 15 per centimeter cube to 10 power 16 per centimeter cube, giving resistivity in the approximate range of 25 ohm centimeters to 2 ohms per centimeters. So here the p-type is here we need to cut from a single crystal of silicon crystal. We need to improve the high purity. We need to add some p impurities such as like boron impurities. Okay, this is the silicon substrate of p-type. So the second case is a layer of silicon dioxide, typically 1 micrometer thickness is grown all over the surface of the vapor to protect the surface, act as a barrier dopant during processing and provide a generally insulating substrate onto which other layers may be deposited and patterned, right? This is the p-type substrate. Now we need to cover the entire surface of this vapor cut with the silicon dioxide layer. Okay, so here we need to cover the entire surface with silicon dioxide layer that is 1 micrometer thickness. Okay, so this silicon dioxide layer will be act as a to protect the surface, act as barrier doping during the processing. And third case here the surface is now covered with the photoresist which is deposited onto the vapor and spun to achieve an even distribution of the required thickness. As I told you here, why we need to cover the entire surface with a photoresist and layer over the surface of this vapor. So here we need to we need to make the device as a required, we need to make the surface with the required thickness. That's why we need to cover the entire surface with the photoresist layer. And if there is any up and downs occur in above the surface, that will be covered by using this photoresist layer. So here we need to cover the entire surface with a photoresist layer. Okay, so this is the photoresist layer is covered over the entire surface of this vapor cut for the required thickness, right? And the fourth point is here, the photoresist layer is then exposed to ultraviolet light through a suitable mask, which defines those areas or those regions into which diffusion is take place together with the transistor channel. So here, after covering the entire surface of the photoresist layer, then that layer will be exposed to ultraviolet light through a suitable mask. Okay, so here we need to expose the entire surface with the ultraviolet light through a suitable mask. So where we need to form the source and drain or the transistor channel, at that area we need to maintain with the shielded mask. Okay, so this is the last step structure here. Now we need to maintain the shielded mask here. So this is the shielded mask here. So where we need to form. So here simply in this area, this point to this point, in this area we need to maintain. We need to form the source and drain region in this particular area. For that purpose, here it will be shielded. Okay, and assume that those areas are exposed to ultraviolet radiation or polymerized. Why we need to why we need to uh, expose these surface with the ultraviolet, right? Because of here this shielded area is exposing, and we need to expose the ultraviolet rays here. The shielded area is unaffected, the remaining area is affected here. So when the remaining area is affected here, this area will be hardened, and it will be protecting if any diffusion impurities are diffused into this particular vapor surface or in p-type substrate. Those diffusion impurities are does not inject in remaining areas, because of the remaining areas are hardened by these ultraviolet rays. So now we need to expose these ultraviolet rays over the surface of this entire surface. So here let us see here, up to this point this area will be affected, this area will be affected. Now this area is going to be hardened and this area is going to be hardened. Okay, and here the shielded area is nothing but it is softened here. Why? Because this area is not exposed through this mask by the ultraviolet ray. So ultraviolet light. So we need to remove this area. Why we need to remove this area at particular place? Because of we need to form the transistor channel, right? So after that, the fifth step, these are subsequently readily etched away together when with the underlying silicon dioxide. Okay, so where the softened area is formed, that will be shielded by the mask, that area will be removed. Okay, and so that the vapor surface is exposed in the window form by the mask. So like this. So here this is the shielded area. Now this shielded area is removed, and this area will be hardened by the unshielded area, unshielded mask. Okay, and here in the sixth step, the remaining photoresist is removed, and a thin layer of silicon dioxide at 0.1 micrometer typically is grown over the entire chip surface, and their polysilicon layer is deposited on top of this to form the gate structure. The polysilicon layer consists of heavily doped polysilicon deposited by the chemical vapor deposition, right? So here in previous case, the remaining photoresist is very hardened. It is not removed, but some by using some chemical techniques, we need to remove the entire surface of this. We need to remove the remaining photoresist layer. Okay, removing the remaining photoresist layer is removed, and a thin layer of silicon dioxide layer is cover the entire surface. Okay, we need to form the polysilicon layer on top of this surface, right? So here the polysilicon layer is covered the here again. Actually the same processing, the step 4 processing going to be here. The entire surface is covered with the polysilicon layer. Again we need to be masked here. We need to expose the mask here. So like this is a mask here, and where we want to make the polysilicon area deposited on the surface, that area is going to be here. Here this area is going to be shielded. So this area is going to be shielded here. So after that, here by applying ultraviolet rays, the remaining area is going to be removed. Where the ultraviolet rays are exposed, that area will be hardened here. That will be available here, right? And then again here, let us see. We need to form the source and drain region. We need to form the source and drain region here by diffusing the N plus diffusion impurities, right? Again, further photoresist coating and masking allows the polysilicon to be patterned as shown in step 6, and then the thin oxide is removed to expose areas into which p-type, n-type impurities are to be diffused to form the source and drain regions. Let us see the structure here. This is a substrate here, and the previous case diagram here it is. Now it is going to be formed. Okay, so let us see here where we want to diffuse the n-type diffusion impurities here. So those area is going to be diffused here by the diffusion process. That is, n plus diffusion impurities are dipped into the diffusion area by the by using suitable gas techniques, right? Now, and then ethic oxide is grown overall again. Ethic oxide is grown overall again, and then masked with the photoresist and etched to expose selected areas of polysilicon gate, and the drain and source areas were connections to be made. Let us see here. This is the region. Okay. Generally, here this is the thick oxide layer. The thick oxide layer is covered the entire surface of the layer, and again the photoresist layer is covered. Again the photoresist layer is covered, and then masking here. Okay, and then masking is given here where we need to make the connection. That area is here. So this area is shielded here, and this area is shielded here, and this area is going to be shielded here, and this area is going to be shielded here. Where we need to form the source and drain regions. Generally, actually here this mark is for connection purpose, but before going to be connection process here, simply this is a mask here. I will show you clearly. Okay, this is a mask here. Okay, so in this area, source and gate, drain, how these areas are etched away together because of the thick oxide layer is covered the entire surface, and then photoresist layer, and then masking. So at particular area we need to be shielded here. We need to be shielded, and this area need to be shielded. These areas need to be shielded. Why? Because to form the source and gate and drain region, and they expose the ultraviolet rays here. Expose the UV light. Okay, so these areas are hardened, and these areas are hardened. This area is hardened. This area is hardened, and these areas are going to be hardened. The remaining areas are softened, where we make the shielded. These are the shielded area. Why we have to make here in these areas for shielding? Because of we need to form source, gate, and drain region. So after completion of this process, the remaining area, the softened areas are removed for the formation of source and gate and drain region. The next step here it is here. Let us see here. The whole chip is then has metal deposited over its surface. So this metal layer is then masked and etched to form the required interconnection pattern. Okay, so here after etched in previous slide there is no metal connection, but now we want to cover the entire surface with this metal layer, and then photoresist layer. Okay, and then photoresist layer, and then masking. Sorry, and then we want to make masking for the formation of connection. So this is the mask. So where we want to make the connection, so that area, remaining area, we need to shield it here. So this area is going to be shielded, and this area is going to be shielded, and this area is going to be shielded, and this area is going to be shielded. Now expose the ultraviolet rays. Now expose the ultraviolet rays. Okay. So expose the UV rays here. The shielded area is softened, and the unshielded area, nothing but affected area, is going to be hardened. This area and this area and this area is going to be hardened. Okay, and the remaining areas are going to be removed. So finally we get in this way, this is the source connection, and this is the gate connection, and this is the drain connection. So after complete processing of metal deposition, photoresistor deposition, masking layer masking, and then exposing ultraviolet rays through the suitable masking, then only after etching, removing, for that we are getting this device, this formation. So this is the complete processing techniques for the nMOS fabrication processing techniques. So here this is a summary of an nMOS process. So what we done in the nMOS fabrication process. So all the steps are going to be as a summary point. The processing takes place on p-doped silicon crystal vapor, on which is grown on a thick layer of silicon dioxide layer. First one, the mask one is patterning silicon dioxide layer to expose the silicon surface areas where the path in the diffusion layer or gate areas of transistor are required. Okay, that is in the deposited thin oxide over all for this reason, right? This mask is often known as thin ox mask, but some texts refer to it as a diffusion mask, right? Why here it is going to be some text refer it as the diffusion mask. For the diffusion process, again it will be going to be act as a mask here, right? And the second mask, the pattern, the ion implantation within the thin ox region where depletion mode devices are to be produced self alignment. And mask 3 is deposit polysilicon overall, then patterning using the processing techniques. And same thing here, using the same mask, remove the thin oxide layer where it is not covered by the polysilicon, right? The mask 3 is here, deposit polysilicon overall, that is 1.5 micrometer thick typically, and the patterning using the same mask and removing the thin oxide layer where it is not covered by the polysilicon, and then diffusion of n plus region into areas where thin oxide has been removed by the transistor, drain, source, or the self-aligning with respect to the gate structure. And the mask 4 grow thick oxide overall, and then each from contact kits. Sorry, each for contact kits. Again, cover the entire surface with thick oxide, and then masking thick oxide, and then photoresist and masking, and then expose the ultraviolet rays. Where we need to form the contact cuts, that areas is affected, and the remaining areas where we need to be make the connections, that area is going to be shielded, and the remaining areas is going to be affected. The shielded area is going to be removed. Why we have to why we need to remove? Because of to cover the entire surface with the metallization. Okay, and next the fifth step here it is mask 5 is deposit metal and then pattern in the mask 5. So deposit the metal layer over all the surface of the crystal surface, and then where we need to make the connection, that area we need to be maintained, and for that we need to make the connection source and drain and gate terminal. For that we need to cover the entire surface with the photo, again with the photoresist layer, and then masking. Where we need to make the connection, that area is not shielded and remaining area is going to be shielded, and then expose the ultraviolet rays. Finally, we get the source and drain regions and gate regions. Thank you.